In production LLM systems, queues are more than waiting rooms. They absorb traffic spikes, protect GPU workers, prioritize urgent requests, and create space for efficient batching. In this module, we'll see how good queue design turns overload from a sudden failure into a set of controlled decisions. So far, we've moved from diagnosing fragile LLM architectures to building a controlled serving platform to adding protective patterns like caching, circuit breakers, retries, deadlines, and idempotency. Now we move to workload control. Queues help the system absorb spikes, prioritize important requests, apply backpressure, and defer or reject work before overload becomes an outage. LM inference is not like serving a static web page. Request time can vary widely based on prompt length, output length, model size, batching, and GPU contention. If every request goes straight to workers, users feel every traffic spike and every backend slowdown. A queue acts as a shock absorber. It turns bursty demand into a steadier stream of work, while giving the platform a place to decide what should be accepted, delayed, prioritized, fairly shared, or rejected early. Treat latency as a product requirement, not just an infrastructure metric. Interactive requests such as chat, autocomplete, support copilots, and agent actions are part of a live user experience. They need short deadlines, fast failure, and protection from long queues. Async requests are different. Summaries, classifications, embedding refreshes, reports, and backfills can wait, which makes them well suited for queues, batching, retries, and off-peak processing. The key design move is to separate these paths, so background work never steals capacity from users who are waiting right now. Before a request enters any queue, it needs a label that tells the system how to treat it. Is it latency-sensitive customer-facing work, a contractual obligation, operational maintenance, an experiment, or batch processing that can wait? This decision should happen at admission, often in the API gateway, orchestrator, or scheduler. Attach practical metadata such as tenant, request class, priority, deadline, retry limit, cost cap, and idempotency key. Without that context, overload becomes messy. Low-value jobs can consume capacity, urgent work can wait, and fairness breaks down. Think of the queue as a traffic control layer. The gateway and orchestrator first classify each request: interactive, urgent, or background. Latency-critical calls may bypass durable storage entirely or enter a very short queue with deadline checks. Async work belongs in a durable queue where it can survive retries and bursts. Worker pools then pull jobs when GPUs are available, using priority and capacity signals. This protects fast user interactions while still keeping expensive model servers busy with batchable background work. When capacity is tight, the platform should not let every request compete in one undifferentiated line. Priority queues create traffic lanes. P0 might represent paid, interactive, or contractual traffic. P1 is normal user-facing work. P2 covers maintenance and background operations. P3 handles bulk jobs that can wait. The goal is service protection. Batch traffic should not delay a customer session or an incident fix. But priority is not unlimited entitlement. Each lane needs quotas, aging, or fairness controls, so lower priority work still makes progress. Once requests are queued, scheduling decides who gets the next GPU slot. FIFO is simple, but one long batch can trap urgent work behind it. Strict priority is useful during outages or safety incidents, yet it can starve normal traffic if left unchecked. Weighted fair queuing is often the production default because each lane gets a predictable share, allowing premium, batch, and interactive workloads to coexist. Earliest deadline first can work when requests carry deadlines, but it depends on accurate timing estimates and clear rules for missed deadlines. Backpressure starts with one question: are we still serving requests within acceptable time? Queue depth shows how much work is waiting, but it can mislead. A short queue of very slow jobs may hurt users more than a long queue that drains quickly. That is why oldest message age matters. It reveals real waiting time. Worker saturation adds the capacity view. GPU utilization, active batches, memory pressure, and concurrency. Strong systems combine these signals with deadlines, then move from normal processing to throttling, deferring, or rejecting before the platform collapses. Admission control is the gatekeeper when demand rises above safe capacity. It classifies the request's priority and deadline, then checks queue age, depth, and system health. If conditions are safe, the system accepts and processes the request. If the work can wait, it can defer it with a 202 accepted response or schedule it off-peak. If quality can flex, it may downgrade to a cheaper model, shorter answer, cache, or degraded mode. If the deadline or policy cannot be met, it should reject clearly, often with 429 or 503, so clients can retry intelligently. Graceful rejection is a reliability feature, not a failure mode. During a launch spike, the worst choice is to accept every request, start inference, and let many of them time out. That wastes GPU time and can trigger retry storms. A better system rejects early when a request is unlikely to meet its deadline. The response should be machine readable, with retry timing, status polling, or an alternative path. For asynchronous work, return 202 accepted and let clients check progress. For interactive users, degrade gracefully with partial answers, cached results, shorter generations, or a clear try again shortly message. For non-real-time LLM work, the cheapest request is often the one that waits a few seconds. Instead of sending each summarization or classification job to the GPU alone, place jobs in an async queue and let workers form batches. That brief wait amortizes model overhead across many requests and keeps the GPU doing dense, useful computation. When possible, batch similar workloads together, because similar token lengths reduce padding waste. The result is higher tokens per second, better utilization, and lower cost per request without affecting interactive latency. Queue workers are where reliability either holds or breaks. A good worker does more than pull the next job. It checks priority, capacity, and whether requests can safely share a batch. That may mean grouping by model, prompt shape, token length, tenant, or request type. Before inference, expired work should be dropped or reclassified, because late answers still burn GPU time. Routing sends each batch to the right model while respecting VRAM limits. If a call fails, retry only within budget, using idempotency keys so callbacks stay safe. Telemetry ties the full path together. A queue is not automatically a safety mechanism. It is safe only when you can see whether work is flowing, aging, or being rejected. Track depth, oldest message age, enqueue and dequeue rates, rejection rate, and latency by priority. Then watch the workers: batch size, tokens per second, GPU utilization, out-of-memory events, and missed deadlines. The most important alerts are age-based, because even a small queue can hide stuck work. Finally, break metrics down by tenant, model, priority lane, and workload type, so reliability decisions also support fairness, cost control, and capacity planning. The main lesson is simple. Queues turn overload from a sudden failure into a controlled decision. By separating intake from inference capacity, they let you protect priority traffic, apply backpressure early, and reject or defer work before failures cascade. For async jobs, batching also improves cost efficiency. Next, we'll protect GPU workers from memory contention and unsafe concurrency.